An entirely new class of transforms were discussed in the previous class. We have seen that in this particular class of transform which we discussed there, the transformation matrix cannot be pre-computed. It is only to be computed after we know that what image it is, that is from the given image or from the given vector. Okay, we have to compose the autocorrelation matrix, that is to say, considering each of the elements to be a random variable, we have to find out the autocorrelation, and then we have to take the eigenvectors and the eigen values for these autocorrelation matrices, and then of these eigenvalues and eigenvectors, or rather of these eigenvectors, whatever transformation matrix we form, okay, that transformation matrix we had considered in the previous class. Now this kind of a transformation, okay, has been described in the literature by various names. Okay, it is known as the Karhunen and Lowe transformation. Okay, in short form it is, most of the people call it as the K L transforms. Okay, and this transform is named after Karhunen and Lowe because for random sequences, okay, it was Karhunen and Lowe, we had who had found out a series summation form, and then the discrete form of this was presented actually by Hotelling, and that is why this transformation is also described in some literature as Hotelling transform. Alright, and because it is extracting the eigenvectors, okay, or rather the principal components, okay, it is also known as the method of principal components. So different books or literatures will be describing the transformation by various names. Some people call it as K L transform, some people call it as Hotelling transform, and some people call as method of principal components. Okay, and there may be subtle variations, okay, between the composition of the transformation matrix from one implementation to the other. Okay, I am not going into the details of that. Rather, let us just recapitulate what we did last time. Okay, last time we had taken a random vector which we were calling as U, okay, and we were calling its autocorrelation matrix. Okay, U was a random vector of size n by 1, and R was the autocorrelation matrix of size n by n. Okay, and we were finding the corresponding eigenvectors phi k. There are going to be totally n number of eigenvalues. So what we got was R matrix product phi k vector was equal to lambda k, where lambda k's are the eigenvalues phi k vector. Okay, and this was true for 0 less than or equal to k less than or equal to n minus 1 for all the integers in k. Alright, now using this phi k's we were forming the basis vectors. These phi k's were the basis vectors of the transformation matrix, so that we had the transformation relations defined as the transform vector V was equal to phi star T matrix, okay, product with U vector, and the reverse transformation was we were obtaining U vector as phi product of matrix phi and the vector V. Alright, now this U equal to phi V in matrix form can be represented in series summation form like this. We can write that this U of M okay, is going to be summation over k equal to 0 to n minus 1. Rather, if I am representing in this form, it will not remain as if I do it this way, phi k vector, okay. Vk times phi k vector if I take and sum it up from k is equal to 0 to n minus 1, what I will get is the u vector, okay. I think this is quite obvious because we are getting the original vector as the summation of all the individual basis vectors, alright, and each basis vector is being multiplied with its corresponding coefficient Vk, okay, which we have seen even for images also. Whenever we are composing the images, okay, we are composing it as a summation of basis. Instead of basis vectors, it will be basis matrices, okay, summation of basis matrices, and all the basis matrices are to be multiplied by their individual coefficients, and by adding them up we were getting the original image back, okay. Even here also the same thing is being done. Now one thing is there, because this phi star t, okay, is a matrix, okay, which is composed of the eigenvectors, or rather the basis vectors of this, which is composed of the eigenvectors of the autocorrelation matrix R, okay, then it follows from the property of the eigenmatrices that if I take the product phi star t, okay, and pre-multiply it by pre-multiplied with R, that is to say phi star t, and this I post multiply by the matrix phi, okay. So mind you, phi star t is the eigenmatrix that I get, okay, and phi is just the conjugate transpose of this one, okay, and R is the autocorrelation matrix whose eigenvectors are being taken to compose this matrices over here, okay. Can you tell me from the property of the eigenmatrices that what it results? It results in a diagonal matrix. Excellent. It results in a diagonal matrix. So I am going to call the diagonal matrix by the big letter lambda, okay. This is the big lambda, okay, which indicates the diagonal matrix, and I am going to write it as diagonal. And can you tell me that what are going to be the diagonal elements of this matrix? The eigenvalues are going to be the diagonal elements, okay. So diag lambda k, this is what I am writing, okay. So obviously this transformation which we have designed, okay, that will fulfill this property that if I pre-multiply the autocorrelation matrix, okay, by phi star t and post multiply by phi, okay, then I get a diagonal matrix composing of consisting of the eigenvalues, alright. Now this idea, okay, this transformation idea can be extended to two-dimensional cases as well, okay. So what I am considering now is that I take an image, okay, whose elements I am denoting by UMN, alright, and let that be an n by n image, okay. So UMN is the element of an n by n image, okay. Then I am considering the matrix itself such that every element of that matrix is a random variable. So what I get is a discrete random field, alright, and for this discrete random field, okay, the autocorrelation function is given by expectation of UMN, okay, product U yet another point in the same matrix, okay, yet another variable which is indexed by m prime n prime, okay, and this, just my notation for writing the autocorrelation function is, I will write it as R m comma n, I put a semicolon over here, m prime comma n prime, okay. This is the representation of the autocorrelation function, rather I call this as autocorrelation, and in these cases 0 is less than or equal to all these m, m prime, n, n prime, all of them, m, m prime, n prime, all 4 of them are lying between 0 and capital N minus 1. Okay. Now, how to form the basis images? Obviously, the basis images are going to be, okay, the eigen functions, okay, which we obtained as follows. Okay. Now, this I am just representing in the series summation form. Okay. Summation m prime equal to 0 to capital N minus 1, n prime equal to 0 to capital N minus 1. I take the autocorrelation function r m comma n semicolon m prime comma n prime, okay, and I take the eigen functions, okay, which I indicate by psi suffix kl, okay, for m prime n prime, okay, and this will be equal to, because these are eigen functions, this will be lambda kl. Now, in these cases, okay, I mean it's eigen values which I get is another 2-dimensional array, okay, which is psi kl, indexed by psi kl, I mean lambda kl, these are the eigen values, and then this multiplied by the eigen function itself, psi kl mn, okay, where as you know already my k and l are lying between 0 and capital N minus 1, and similarly m and n, okay, they are lying between 0 and capital N minus 1. Okay. So, this is the relationship which I am going to get, okay, if I just write it in the usual summation form. Okay. And if I want to write it in a matrix form, of course the representation is going to be simpler. So, what I am going to do is that, since it is an n by n image, alright, I am going to just represent it in the form of an n square by 1 dimensional vector, okay, and I will take the transformation matrix size as n square by n square, and I will get a transformed vector of size n square by 1. Okay. So, let us write down in that form, okay, or rather before, yeah, fine, I mean we can just do it this way. In that case, okay, let us write it in this form. Okay, psi i's, okay, psi I is an n square by 1 dimensional vector representation of psi kl mn, okay. Whatever I was calling as psi kl mn, okay, this was of dimension n by n, okay, and instead of that I am considering the n square by 1 dimensional vector, which I am calling as psi I, okay, and I am calling and psi I is going to be basically the eigenvector for which matrix? This Cal R matrix. This is the Cal R, okay, and Cal R is basically, this is an n square by n square autocorrelation matrix. Autocorrelation matrix. Matrix of what? This is the autocorrelation matrix of what? The image, okay, the image not in the 2-dimensional form, that is to say not the image in the n by n form, rather the image when mapped into the n square by 1 dimensional vector. Matrix of the image mapped into an n square by 1 dimensional vector. Okay. So basically this relation which I am getting, okay, is again the same relation which I had got in the case of the one dimensional transformation. That is to say, this was our basic this followed from the basic property of the eigenvectors. Okay, if lambda i's are the eigenvalues and psi i's are the eigenvectors, okay, then we were getting this relation, okay, even in the earlier case also. But the only difference is that here the image matrix is n square by 1 dimensional, even the autocorrelation matrix is going to be n square by n square dimensional. So if I want to now represent a 2-dimensional function, okay, then what should I do? I should make this thing as separable. Okay, as before I am going to make it as separable. So I define this K L R and this psi matrix, okay, I can represent as the Kronecker product, okay, of two matrices. Rather I am going to call this K L R matrix as the Kronecker product of two matrices R1 and R2. In that case, tell me what is going to be the size of this R1 and R2 matrices? They are going to be, so both R1 as well as R2 matrices are going to be of size capital N by capital N, okay, and the matrix psi, okay, I am composing as the Kronecker product of phi 1, matrices phi 1 and matrices phi 2, and again this phi 1 as well as phi 2, okay, they are going to be of what size? They are going to be n by n, okay, so that now I can write, okay, the transformation by the usual separable transformation relationship. All right. So pardon please. This is psi. Basically, I mean any psi is to be represented by the product of phi 1 and phi 2. All right. So this is written as phi 1 star transpose u phi 2 star, okay, and the reverse transformation u can be written as phi 1 v phi 2 transpose. All right, these are going to be the transformation expression. Of course, one point must be borne in mind, that whenever we are forming the composing this K L R matrix and this psi matrix as the Kronecker product, okay, individually these relationships will be satisfied. Rather I should have, okay, phi j r j phi j star transpose, okay, that should be equal to the capital lambda j, okay, and this I am going to have for j is equal to 1 and 2. That means to say individually both for phi 1 and phi 2, okay, rather phi 1 is going to be the eigenmatrix, phi 1 star phi 1 star transpose is going to be the eigenmatrix for R1, okay, and phi 2 star transpose is going to be the eigenmatrix for R2, okay. This must be satisfied, okay, while forming the Kronecker products, and if that is satisfied, then we are going to write this relationship, okay. It is fairly simple to see. This is an n by n matrix, and this is pre multiplied by another n by n, post multiplied by another n by n, and V remains as an n by n matrix over here, okay, and similar is the case with the reverse transformation. So this I will call as the K L transformation pair. So this is the K L transform pair in 2 dimensions. Yes, please. No, 1 minute. If I am taking psi I, that is a vector. Okay? But using those psi i's, whatever matrix I am forming is the matrix psi. Okay? Please understand this difference. Any questions here? So this is the separability which we considered. Okay? And now we are going to see some of the properties of KL transform. And after I tell you about the properties, you will understand that why at all we are going in for this kind of a transformation. Okay? Rather, what are the advantages that we get by taking this transform. Okay? The first property which we are going to study is the decorrelation in the transform domain. Okay? Decorrelation in transform domain. And the thing is like this. Okay? The KL, after undergoing the KL transformation, we are getting the vector V, okay, which is indexed by K, okay. Vk is the transform vector, okay, where K is equal to 0, 1, 2, etc., up to capital 1. So this set, okay, represents the transform vector, okay. And the decorrelation property says that these Vk's, okay, are uncorrelated, okay. They are uncorrelated and they have a zero mean. This is a very, very important property. The transform vector which I get is a decorrelated vector, okay, and it has got zero mean, okay, and this is a very important property I said. So that means to say this sentence which I had just now written down, okay, can be represented in the mathematical form as mean is equal to 0 means how am I going to represent? Expectation, I am going to write expectation of Vk equal to 0. So this itself confirms that it's a zero mean random variable, okay. And how to find out the correlation? The correlation will be, yes, expectation of Vk into V star of L, okay. Expectation of Vk and V star of another element L, okay. This is the correlation, and if it has to be decorrelated, then what does it mean? Decorrelated means unless K is equal to L, okay, it is going to be 0. The correlation value is going to be 0. But if K is equal to L, then it is non-zero, okay. That is the property of decorrelation. So I am going to represent the this particular function by a delta function, okay. Delta of K minus L I am going to write, okay. And only if K is equal to L, okay, then the correlation will be given by what? Tell me. By the eigenvalue. The eigenvalue will give the correlation. So this will be written as the kth eigenvalue, that is the lambda k, okay, times delta K minus L, okay. This is going to be the second property. So that means to say we have to prove that expectation of Vk equal to 0 and expectation of Vk V star L is going to be this expression, so that when K is equal to L, then it is non-zero, okay, and if K and L are unequal, then this is equal to 0. Now decorrelation is very important thing. I mean, if in the transform domain the vector which I get is decorrelated, then obviously I need to take only a few vectors, okay, a few vector samples from the transform domain in order to reconstruct my original vector, okay. And it is found that if it is correlated in the original domain, or rather in the if it is correlated in the original domain, it is decorrelated in the transform domain. This we have been seeing for the other transformations also. Now, how to prove this is very simple. I will give you the simple proof of this. Okay, you consider the definition. Our definition for this K L transform is that V was written as what? Phi star transpose U. All right. So, what is going to be my V star transpose? Yes, U transpose, I mean by property of transpose itself one can get, it is U transpose, no, not U star, this is U star transpose, because I am going to take V star transpose, so it is U star transpose into phi. Okay. So, what is going to be expectation of V Vt, V star T, okay. If I am considering the expectation of V star T, okay, then this is going to be the autocorrelation of the, output vector, okay. So, this can be written as, yes, tell me, I already have the expression for V vector and for V star transpose vector. So, it is going to be phi star T of course does not have any expectation, okay. Even the post multiplication also is to be done by phi over here, but in between I am going to have the expectation of U transpose, U star transpose, okay. What is this? What is the middle term? Expectation of U transpose, U star transpose. That is the autocorrelation matrix. What I am writing for the autocorrelation matrix? The matrix R. Okay. So this I can rewrite as phi star T multiplied by R multiplied by phi. And just now, I think today only, we saw that what it is. It results in a diagonal matrix. Diagonal matrix consisting of the diagonals, and the diagonals happen to be the eigenvalues. Okay, so it's a diagonal matrix consisting of the eigenvalues. So this is going to be the big lambda, okay, which is the diagonal matrix, and which I had already seen as this is the diag of lambda keys. So we are getting what I want. So since it is a diagonal matrix and all the non-diagonal elements are going to be 0, okay, so it obviously follows that unless K is equal to L, okay, we are going to get the autocorrelation of the output sequence as 0, okay, and only if the diagonal, only if this K and L are equal, okay, that corresponds to the diagonal elements, okay. That is to say, we are considering correlation of a variable with itself, okay, which is given by the lambda K, okay, and that leads to the non-zero elements, or rather the diagonal elements of this matrix, okay. So we have proved what we wanted to, okay. Any questions?
Why it is coming up? There is not any
Sign?
expectation. That expectation is hard. Why it is coming up? I start from the expectation.
No, 1 minute, because in this case, while composing the R itself, okay, I am considering the expectations, okay. The R matrix which you are getting, that itself is the result of these expectations, okay, and these phi's are composed from R only. I am composing the phi star transpose from the eigen vectors of the autocorrelation matrix, okay. Now, one point which should be noted over here, that it does not obviously prove, the proof which I have given, okay, just now, it does not obviously prove that the K L transformation matrix is the only matrix, okay, which decorrelates the output sequence. There could be existence of other matrices, other transformation matrices as well, okay, which can decorrelate the output sequence, okay. But at least one property we have clearly seen, that K L transform does it. It decorrelates, it decorrelates the output sequence. And now we are going to study something, okay, which will be very useful to us, in the sense that I have been always talking of the image compression application, okay. That is to say that if it is possible, okay, from the transform domain to reduce some number of samples from the transform domain, okay, and then we can represent the original vector from a reduced set of samples in the transform domain. If we can do that, obviously our objective is getting fulfilled, that is to say we will be able to have the data compression. So now we are going to consider a system like this, okay. The system is, at the input to the system I am giving a u vector, alright. The u vector is being fed as an input to the system, and the system is having the first block which is making a transformation A. So there is a transformation A, okay, and A is of size n by n, obviously, okay. And what are we going to call as the output of this transformation? Simply V, the vector V, because we have been all along writing that the transformed vector V is equal to A u, okay. Now if I had put yet another block A star transpose over here, okay, just now if I had put yet another box A star transpose, then at the output I would have got again the u vector back, okay. But I am not going to do that, okay. I am not going to keep an inverse transformation function over here, okay. Instead of that, I am keeping a matrix which I am calling as Im, okay, which is of size n by n. The matrix that I have put over here is the matrix Im, okay. And let me tell you what this Im means. What do I call as the I matrix? I matrix is the usual identity matrix, okay. So identity matrix, which you already know, that all the diagonal elements are 1 and the rest of the elements are all zeros. And in the case of In, what I am doing is, I am not making all the diagonal elements are 1. I mean, of course, all the off diagonal elements are still zeros, okay. That means to say, here all elements are going to be 0, here all elements are going to be 0, okay. But the off diagonal elements, in the case of identity matrix, all of them are 1s, okay. That means to say, for row number 0 to row number capital N minus 1, everything is 1 for identity matrix. But in this matrix In, only the first m elements, only the first m diagonal elements are 1s and rest of them are zeros, okay. Like in this particular case, we will consider it this way, that supposing I make this element as 0 and this element as 0, and the rest of the diagonal terms, that is to say, this is a 5 by 5 identity matrix, in which I have made the first 3 diagonal terms as 1 and the last 2 diagonal terms as 2, okay. Then I am going to call it as I3, okay. That means to say that out of the capital N number of diagonal elements, I am preserving only small m number of them, okay. So whenever I am writing the Im matrix, okay, please keep in mind that m is less than or equal to capital N, alright. So since I am multiplying it by the Im matrix, okay, can you tell me that what results at the output of this? Just the V vector Alright? The V vector is getting multiplied with this In transformation matrix. The first n terms of the V vector will be preserved, okay, and the rest of the terms in the V vector will be made forcibly equal to 0. Okay, that means to say that I am taking a reduced set of samples from the output vector. Alright, so this results in a new sequence, and I am going to call that sequence as W. So I am considering that the output of this is a W vector. Had this been an, if this had been an identity matrix, then I would have got W vector same as V vector, but since it is not exactly an identity matrix, the last few diagonal terms are being made 0, it results in a vector like this, where the relationship is very simple to see. Wk will be equal to Vk, okay, as long as k lies between 0 and m minus 1. So if k is less than or equal to, if 0 is less than or equal to k is less than or equal to m minus 1, then we are having Wk equal to Vk, and Wk will be equal to 0 otherwise. That is to say, for k greater than or equal to m, Wk is going to be 0. Okay. So I had the n dimensional sequence in V, okay, and I am just eliminating, okay, the last few samples from it and preserving the first few. Okay. So that means to say, from an n dimensional vector, alright, I am moving into a small m dimensional subspace. This W vector, okay, is actually restricted to an small m dimensional subspace. Small m dimensional subspace in N. Okay. Now what I am going to do, okay, after eliminating some of the samples, I am going to put it through a reverse transformation. Okay, and I am considering the reverse transformation matrix to be a matrix B, which is again of size n by n. Okay, if I do that, in a normal course you well understand, if this transformation is going to be a unitary transformation, then it is well known to you already that this matrix B is going to be the A star transpose, alright, in the case of unitary transformation, but I am going to consider this B matrix, okay, in general. Okay, so this is the reverse transformation matrix. If I do that, what sequence do I get? Do I get back the U exactly? I will not get U exactly, but I may get something quite close to U, isn't it? Okay, because after all the forward transformation is there as it is, the reverse transformation is there as it is, and in between the middle block which is there, it is only chopping off the last few samples in the transform domain. Okay, so let me say that the output is a Z vector, alright, the output is a Z vector. So now my U vector is not exactly same as the Z vector. There is going to be some amount of error between the U vector and the Z vector. So we are going to consider the case, okay, we are going to consider the mean square error between this U vector and the Z vector, okay, and then we will see that in what manner these transformation matrices A and B should be defined so that the mean square error is minimized. I repeat what I said. I am going to consider the mean square error between this U vector and the Z vector, alright, and then I am going to see that how should I design this A matrix and B matrix such that it results in the minimum mean square error. Alright. And interestingly, it so happens that the transformation matrix that results, that happens to be the K L transformation matrix. It so happens that A becomes phi star T and B becomes phi. Okay. So it is unitary and it is the same K L transformation matrix. So that means to say what? If you want to have the minimum mean square error between the original vector and the vector which you are getting, okay, by going through the reverse process. Of course, the only difference that we have done is that we have passed it through this IM matrix where the last few samples have been removed, okay. So, if I want to consider the mean square error between this U and Z, the transformation matrix which must be designed should be the K L transformation matrix, okay. So, which means to say that K L transformation is what? It is an optimal transformation. K L transformation is an optimal transformation, okay. We can manage with fewer number of samples in the transform domain, okay. Let me represent the problem a bit more analytically. Actually, the mean square error expression is, okay, let me write the average mean square error, okay. So, this Jm which I am writing is average mean square error. And why I am indicating this suffix m? That is very simple, because the error is coming because I am keeping only m terms out of capital N number of diagonal terms. So, by definition of the average mean square error, I can write it as 1 upon n expectation of summation n equal to 0 to capital N minus 1 mod of un minus zn square. Alright, okay, and this happens to be same as 1 by n. In the matrix form, I can write it as the trace of the expectation of u vector minus z vector multiplied by u vector minus z vector star transpose, okay. Okay, trace of this matrix, if I take, then I get the average mean square error, okay. And we have to design, the problem is that we have to design the transformation matrix, okay, A and B, which results in minimum value of Jm. So, how to design A and B matrices by minimizing Jm, and mind you, this Jm is to be minimized for every value of m. And what is the range in which the value of m can lie? 1 to n, or rather you can say 0 to n minus 1, okay, 0 to n minus 1, or rather, since m is the number of samples that I am preserving, let me call it as m lying between 1 and n. Alright. Now, this minimization, okay, is actually achieved, as I told you the result already, this is achieved by the K L transformation. I am not giving the proof over here, okay, and I request you to, I mean, if you are interested in knowing the details of the proof, okay, it is very well given in AK Giant's digital image processing book, okay. In AK Giant's digital image processing book, they have given the proof for this expression. If you are interested, please refer to this, okay. But we take this result as it is, okay. That means to say that we now consider always that the average mean square error is going to be minimized when we consider this A and B transformation matrices as the K L transformation matrix, alright. And then, so we were basically studying the property of the K L transformation. So the second important property which we had seen was that if we take, if we consider only m number of samples, okay, in the transform domain, okay, then the average mean square error is going to be the least for the K L transformation, okay. And the third aspect is also the third property is very much important, okay, and this all again follows from the results of the earlier property itself, that is to say about the distribution of variances. Now, it is seen that among all the unitary transformations, if we consider the unitary transformation V equal to AU, okay, among all the unitary transformation, okay, phi star t, okay, phi star t, that is to say when A is equal to phi star t, okay, then it packs maximum amount of energy in the first m samples where m is less than or equal to n, okay. So let me write down, among all the unitary transformations given by V equal to AU, the K L transformation phi star t, okay, packs the maximum energy, maximum average energy in m less than or equal to capital N samples of V. Okay. So this also makes the K L transformation very attractive, okay. So that means to say K L transformation, okay, gives you the, out of all the unitary transformations which are known, okay, K L transformation gives you the best performance in the energy compaction, right, okay. Here also I am not going into the details of the proof, just formulating this mathematically. So what we are actually representing is that we are defining, okay, sigma k is like this, sigma k square. By definition, the sigma k square, the variances, okay, are being defined as expectation of Vk square. Obviously, I can call it as variance, I can call it as energy. Alright. So, now what happens is, yes, one thing is very important. How are we composing the K L transformation matrix basically? As I told you that we are considering the first k eigenvectors, the n number of eigenvectors we are considering, okay. Now there are totally n number of eigenvectors available and we are composing the transformation matrix from those eigenvectors, okay. Can I pick up the eigenvectors haphazardly and put them? It's not being done that way, okay. It is seen, okay, if you go through the proof of the earlier property, you will see that for optimal results, what we must do, it is very important, okay, we must sort the eigenvalues first in a decreasing order. The eigenvalues will be sorted in a decreasing order and then the corresponding eigenvectors will be placed one by one, okay, one after the other, and then the transformation matrix which you get is the optimal K L transformation matrix. So I am assuming that always this lambda 0 square is the maximum, then lambda 1 square is the next, lambda 2 square is the next, like this. So lambda 0, the modulus of lambda 0 must be, lambda 0 square is greater than or equal to lambda 1 square is greater than or equal to lambda lambda 2 square, like this the relationship will follow. So, if we are defining the transformation matrix that way, then it follows that the sigma square k, okay, will also follow the property sigma 0 square is greater than or equal to sigma 1 square is greater than or equal to, and so on up to sigma n minus sigma square n minus 1, okay. And I am considering the sum of all these energy terms, not all the energy terms, rather the first m terms, okay. So, I am considering the summation of the m terms, okay, and which I am defining as the summation k is equal to 0 to small m minus 1 sigma square k, okay. Then I mean I am just writing the matrix A because I have to now see that what should be the composition of this matrix A, so that this summation is what, minimized or maximized? This summation must be maximized, okay. I must pack maximum amount of energy in the first m samples. So, I have to see that what should be the form of this transformation matrix A, so that this SMA is maximized, okay. So, then I mean the third property says that then for any fixed m lying between 1 and n, okay, Sm of phi star t, okay, that means to say when A happens to be phi star t, so Sm of phi star t, that is to say taking the KL transformation matrix, okay, it is always greater than or equal to Sm of A. So, in terms of energy compaction, I repeat, in terms of energy compaction or compacting the maximum amount of energy in the first m samples out of capital N, okay, the KL transformation matrix gives us the optimal performance, okay. KL transformation matrix is best among all the unitary transformations in packing the energy or in maximizing the energy in the first m samples. Is it clear? So, with this, okay, we conclude the KL transformation matrix discussion. Of course, one point should be remembered by you. All the earlier transformations which we had discussed, that is to say the DFT, the DCT, then the Hadamard transforms, okay, all of them are fast implementable, okay. They can be implemented in order of n log n complexity, okay. Now, in all such previous transformations, the transformation matrix can be pre-computed beforehand, okay, whereas in this case the transformation matrix is to be computed, okay, from the data itself, okay, by looking at the correlation of the data, the transformation matrix is to be computed. So, that is why there is, I mean it is not possible to have the fast transformation, okay, in that conventional way. So, a conventional KL transformation is not fast implementable. So, that gives us some disadvantage as compared to the other transformations, because if one considers the computational simplicity, okay, then rather one should go in for the earlier transformations which we had talked about, okay. But of course, if we are talking in terms of performance, I mean if we can tolerate the computational time that gets involved in the computation of the transformation matrix, and thereafter after computation of the transformation matrix you have to do the transformation itself, okay. All these processes, okay, if you can tolerate the computational time, then KL transform is going to give you the best performance of them, okay, but it is not fast implementable. Of course, in recent times, okay, lot of research works have been put up, okay, to implement the K L transformation using fast algorithms. Now, in that case, what they do, that the image matrix, okay, instead of taking it as a single discrete random field, okay, it is stochastically decomposed into two random fields, okay, and for the first random field we implement the K L transformation in a fast algorithm using what is known as the sign transformations, okay. Using the sign transforms, okay, one can implement the K L transformations, okay. That is to say, of the stochastic decomposition, the first part can be solved using the fast K L transformation, okay, and the other part can be taken care separately, okay. There has been lot of research efforts, even the literatures and all the recent journals have reported, okay, some of the fast implementation of the K L transformations. All right, we are not going into those details, okay. If you are further interested, look at the recent, over the last 4-5 years, the issues of the IEEE transactions on acoustic, speech and signal processing, or very recently the IEEE transactions on signal processing, okay, IEEE transactions on image processing. All these journals you can refer to if you want to be knowledgeable about the fast K L transformation implementations. Now, in the next class, now that we have completed all the various kind of transformation techniques, okay, all the major ones rather, we are going to make a comparison between all these transformations, the performance comparisons in the next class, okay, and that will be the concluding lecture, okay, on the image transformations. Thank you.